In several videos on this channel, we featured the Meta AI Yann LeCun discussing a future of AI based on learning from the real world, particularly the world represented in videos. Only a couple of years ago, this scenario looked very challenging. But Yann LeCun was at VivaTech 2025, and this was probably one of the very first industry events in which LeCun talks about the VJPA2, the Video Joint Embedding Predictive Architecture. Let's hear the definition in his words.
It's a model that attempts to advance along at least three dimensions, three challenges of AI. The first one being AI systems that understand the physical world. The second one, systems that are capable of reasoning. And the third one, capable of planning. So those are three major obstacles or challenges that we need to kind of overcome to have AI systems that go to the next level. And so VJPA is one of the first systems that can really learn how the physical world behaves by being trained to predict videos, essentially, right? So show it a piece of a video and corrupt that video in some way. You can mask a piece of it, or just mask the future, the second part of the video, or just a whole chunk of it, and then train a system to fill in the blanks, basically predict what is missing in the video. Now, we've been trying to do this for many years. In fact, this idea of this is a particular instance of self-supervised learning, and it's really what has powered the success of large language models. And we've been trying to work on this for video for 10 years. Actually even more, but and it's been a bit of a failure until recently. And the reason is that although it's easy to kind of predict the words that are going to follow a particular text, which is why LLMs are working so well, you can't do this with video. If you train a system, you show it a piece of video and you ask it to predict what comes next, there is no way you can predict all the details at the pixel level of what goes on in this video. And so the JEPA idea, that means Joint Embedding Predictive Architecture, and the V stands for video, basically does not even attempt to reconstruct pixels. It attempts to learn a representation, an abstract representation of the video, where a lot of the details are eliminated, so that the system can make predictions in that representation space. That's the basic idea of JEPA. And then we've been trying to apply this, sort of finding recipes to train those things, at the large scale, and apply this to sort of various domains, not just video, but just about everything.
JEPA empowers AI to understand physics, reason about consequences, and plan actions. Planning and reasoning are the next steps for VJEPA, and are essential steps for models to reason and make decisions without training. This will be very important in robotics.
So world model is something that tells you, given the state of the world at a particular time, that you can observe from a short clip of video, and given an action that you imagine a robot taking, could the system predict what the state of the world is going to be after the action has been taken? And so if you have this kind of world model, you can, a system that has this model of the world can imagine the consequence of a sequence of actions, and therefore can figure out a particular sequence of actions that will fulfill a goal, that will accomplish a task. That's planning. So that's one of the big challenges that AI systems should be able to do. And planning and reasoning are really the same thing. So this could give us a blueprint also for systems that are capable of reasoning. And what we've shown with VJPA V2 is that when we train such a world model, we can use it to basically plan the motions of a robot arm to grab an object or open a door or something of that type. Those are not particularly complicated tasks, but what's interesting about it is that the system can basically learn or can accomplish those tasks without being explicitly trained to do those tasks. It's just using its world model to predict what the consequences of its actions are going to be.
In the past, LeCun has also been critical of current LLMs because they can't really reason. He is still of the same opinion.
Everybody is talking about AI systems that can reason, AI systems that can plan, agentic systems that can take actions. To be able to take an action reliably, you have to imagine be able to imagine what the result of those actions is going to be. If you take a sequence of actions blindly and you don't know what the effect is going to be, you're going to make some mistakes. And so current systems, LLMs don't have those internal world models. They're basically planning blindly by just kind of pretty much regurgitating plans they've been trained to do or produce. If you have this concept of world model, and a lot of people in AI are working on this at the moment, then the system can just project, imagine, what sequence of actions, what is going to be the effect of the sequence of actions, and then plan to accomplish a particular goal. Now, there's still a lot of challenges there on the way. It's not like we've solved the problem, and this approach also connects with some classical work in robotics, in motion planning. The difference here being that those world models are trained from data, and it's completely unsupervised. There is no labeled data or nothing like that.
Also, consistent with previous conversations, LeCun rejects the term AGI because it is based on a concept of individuals with generic intelligence. What the AI industry calls AGI, at Meta is called ASI and AMI, or AMI. Here is the meaning.
So I don't like the phrase AGI, okay, because it's used to designate systems that have sort of human-level intelligence, if you want. And so that relies on the assumption that human intelligence is general. And I'm sorry to say, human intelligence is not general at all. We're very specialized. Slightly more general than most animals, but some animals are smarter than us in certain areas, and certainly computers can solve certain tasks much better than we can. So that means in some way we are specialized, right? So I prefer these two phrases that we use at Meta. One is ASI. It's a little scary. It means artificial superintelligence. It means, okay, by the time that we get to human-level intelligence, we can get past. And in fact, we already have a number of tasks where machines are already superior to humans. So that's what we should be talking about. And superintelligence doesn't mean it's general. It just means it's slightly better than humans in most domains. And then there is a second phrase that we use, and it's AMI. We actually pronounce it the French way, ami, which means friend. And that's basically our blueprint or a plan to reach ASI. So there's a long-term plan in the company to basically produce AI assistants that are as smart as humans or perhaps better, that will help us in our daily lives. This is a challenge that we set for ourselves 10 years ago, and now, but it was really sort of exploratory research at the time, and now it's become more of a kind of a product strategy, if you want, even though we don't know how to do it yet. We're kind of starting to see the end of the tunnel, so it's becoming real. And so the AMI plan is a set of techniques that some of us have been working on to basically overcome those four challenges I was talking about. Systems that understand the physical world, have common sense, if you want, have persistent memory, can reason, can plan, and also a fifth one, which is systems that are controllable and safe. So basically you give them a task and they accomplish that task, and that's it. They don't do anything else.
And in talking about the future, agentic AI is also a scenario envisioned by Meta, and history shows that innovations like agentic AI come not to add risks to our daily life, but to assist humans to perform better in many tasks.
So you can buy a 30-euro gadget that plays chess and will beat you at chess, which means humans are not very good at playing chess. Similar for Go and poker, and there's a number of games like this where computers are just better than humans. But it's also true of, solving equations, computing integrals in mathematics, or finding the best path in a map to go from one city to another. Right? We're used to this. Like the machines are better than us at this. In fact, that's really what we should work on. Machines that are better than us at certain tasks for which we're not particularly good, right? That's the best way to assist humans with computers. That's actually the history of computers, really, using computers for things that humans are not particularly good at. So it's just a continuation of this, where, in a future in which, like, all of us will be walking around with smart glasses or other smart devices, within which there will be AI assistants that we can talk to, we can ask any question, Maybe they display informations in the glasses and things like that. And that will sort of amplify your intelligence, if you want. It's like having a staff of really smart virtual people kind of working with you at all times. You know, all of us will be like, you know, a CEO or a minister or a university professor, you know, with a staff of students who are smarter than themselves. So, you know, it's empowering. A lot of people kind of feel threatened by it. I think it's really empowering to work with people or machines that are smarter than you. Now, we want systems of this type that are agentic, so they can sort of, you know, act in the digital world at least. We want perhaps systems that have a mental model of the user they're talking to, so they're not telling us things that we already know or that we're not able to absorb, right? So those systems will have to have some mental model of what we know, what we don't know, you know, what we are capable of digesting, what kind of information we could be interested in. And systems that can, you know, plan sequences of actions that might be complicated, you know, making reservations for, you know, travel and stuff like that. And then eventually also kind of similar things for the physical world. Domestic robots, robots of various types, and Meta is actually getting involved in robotics in sort of a big way. And then in between there are things like code writing, okay? So we have systems, I mean, this is probably one of the biggest applications of LLMs at the moment is helping software developers write code. And there is one issue with this, which is that very often when the code is produced, it's globally maybe correct, but not completely correct. You have to kind of fix some bugs and kind of change a few things. And those are generally relatively simple pieces of code, right? You can't ask a system to design new algorithms or figure out a data structure for a particular problem that they've never seen before. They're basically kind of regurgitating code they've seen, you know, over the corpus that they've been trained on. What we want is, and that's what we're working on, a system that can imagine what the result of executing an instruction or making a function call will cause to the state of the program, and then plan a sequence of instructions to arrive at a particular goal. So it's very similar problem that I was talking about earlier, the ability to plan, to imagine what the consequences of your actions are. That's required for dialogue systems, for agentic system, for code generation, and certainly for physical robots.
And when we will see significant changes in the next 3-5 years, according to LeCun. And this is in line with other predictions in the same domain that we will present in the upcoming video. This is a good time to subscribe to this channel.
You know, generations of AI researchers have been consistently wrong about this kind of estimate. So, okay, my story would be if all the planets lined up, if all the techniques that we are imagining developing work out, we're encountering the kind of usual difficulties in developing them and scaling them, we're going to have a good handle on whether this kind of JEPA approach is really going to take us there within 3 years. And then within 5 years, probably some, you know, early results or prototypes that may have systems that really understand the physical world, perhaps at the level of a cat or a rat or something like this, right? And then we're going to work our way up towards systems that can also, you know, plan not just in the sort of low-level physical world, but also in sort of abstract domains, perhaps connected with language or connected with mathematics or with geometry or things like that, right? And maybe reach human intelligence at some point, but it's almost certainly harder than we think. That doesn't mean we're not going to have useful, you know, artifacts on the way to there. So I think we're going to start seeing kind of the more tangible applications of this maybe within 5 years or so.